Thank you. May I have the slides? Great. Well, thank you very much for this wonderful conference and for giving me the opportunity to present our latest work. I'm working in between two institutions in École Normale Supérieure and at Meta, where I lead the brain team, which interfaces two disciplines, neuroscience and AI. And before I start, oh, that's not the last slides, but okay, that's going to be tough if they didn't use the right ones. Okay, before I start, I want to stress that the work that I'll be presenting is the result of a collaboration effort, both within the company, but also with academic partners with whom we work on the theoretical ideas, of course, but also who actually collect the data that we analyze. So I'm immensely thankful to them. So I thought I would take an unusual approach to the presentation and start right away with a result. What you see here is something similar to what Stanislas presented earlier, where participants in the 7 Tesla MRI scanner were watching images across 37 sessions of 1 hour. So that's a lot of recording time. And for each fMRI activity, we can try to train an AI pipeline to try to reconstruct as accurately as possible the image that they perceive. And the results were really astonishing from my point of view, because I think many of us in the community didn't think that this level of accuracy would not be achievable. And this is in part the motivation behind this title, which is a reference to a famous essay by Eugene Wigner, a theoretical physicist, who ponder on the unreasonable effectiveness of mathematics in the natural sciences. And so this is troubling in a sense because it was unexpected to see that these AI tools are that efficient at tackling these complex issues in neuroscience. We do see the use of AI in pretty much all scientific disciplines, and that's kind of a technical tour de force, which is very impressive. But I think in this particular case, there is something much more interesting than the technical tour de force, which is the actual reasons why this works in the first place. And to sort of entertain this idea, I think it's important to stress that in AI and neuroscience, we have this kind of interesting historical relationship where we have a common goal, which is to try to understand the principles of intelligence. So we don't just use AI as a technical tool to process complex data, but we also use essentially these AI systems to understand the machinery, the mechanisms underneath intelligence. And what I'll try to illustrate today with a few studies is this, I think, arguably surprising observation, which has been made across many labs now, that modern AI systems tend to converge to the functions of the brain. So what do I mean by this? Well, for instance, if you train a neural network, a deep neural network, to process speech, you can evaluate its activation to show that these hierarchy of representation that the neural network will eventually learn correspond to the hierarchy of speech processing in the brain. This is here a study that we published with Juliette Millet and Charlotte Koster at NeurIPS last year. And the way by which we approach this, or the method that we follow to make this demonstration is by comparing the activations of a standard self-supervised neural network in this case. So it's a neural network which is not trained with any annotations. So it just basically hears a lot of speech sounds. And the goal of this network is to predict its own internal representations, which is one of the ways by which you can learn to process information without supervision. And so we compare the activations of this kind of AI network to the activations of the human brain in response to the same speech sound. In this particular study, we focused on a state-of-the-art model, which was released at Meta. Wave2Vec2 is still a pretty strong model. And we compare the activations of this particular model to the activations that we can analyze with fMRI. This is after curating a bunch of public data sets where participants were listening to natural stories like The Little Prince that was collected at Neurospin in Paris and in other centers, but also a variety of different fictional stories. And of course, the comparison between the activations of an AI systems and the activation that you can collect with fMRI is, this comparison is non-trivial. It's not necessarily easy to make because you don't know a priori which neurons presumably correspond to which part of the model. And so for this, you can use a very standard procedure nowadays, which is called encoding, which is just a linear regression that given the activations of let's say the AI systems, X, you're trying to predict the activations in fMRI in response to the same speech input, Y. And so here is an example to illustrate this analysis, where on the horizontal axis is the time from the onset of a story that the participants were listening to in the scanner. And the vertical axis is the amplitude of the bold response. And the black line is the actual bold measurement, whereas the red line is the result of this linear regression. You can think of this as a virtual neuron in the AI system. And so the black line, the true brain measurement, and the virtual neuron seem to be following a similar trend. And so if you were to correlate the two, they would tend to be decently correlated, meaning that they capture the same function. In response to the same input, they tend to have the same output. Now, this is actually a cherry-picked result here. This is the best voxel that we can get because we can repeat this analysis for each voxel separately, and you end up with this kind of correlation map, which indicates in the brain the areas or the response, which can be linearly predicted from an AI systems like Wave2Vec2. Because we work with a significant number of participants, statistics is not too much of a problem, and here the effects are thresholded at 10 to the minus 10, which is pretty conservative in our field. And overall, what it shows is that the effect is strongest in the expected set of regions, so around the primary and secondary auditory cortices, the belt, parabelt, even though these effects are actually significant pretty much everywhere in the brain. So that's not that interesting to do this analysis in this way. What is much more interesting is to do it, if I manage to click on the next slide, to do it layer-wise. So when you do this analysis layer-wise, what you're trying to do here is to evaluate the extent to which each voxel in the brain can be linearly predicted from, let's say, the first layer of your deep net, second layer of your deep net, third layer, and so forth. And in this particular case, we showed which layer is best at making this prediction. And so you see a pretty clear gradient. You see that in the early auditory areas, the voxels are color-coded in blue. And this means that their activations in response to natural speech tend to be most similar or best linearly predicted from the early layers of this transformer. Whereas if you take high-level areas, in particular the anterior temporal lobe or the many areas in the prefrontal cortex, including the IFG, the inferofrontal gyrus, and I should say perhaps precuneus for Joseph here, these voxels are color-coded in red, meaning that their activations seem to be most linearly correlated with the deepest layers in the network. Now, from a purely neuroscience point of view, that's kind of interesting. We can also see additional gradients. If you look carefully, there is something that starts in the primary motor cortex, presumably around the larynx area. There seems to be a gradient that goes towards the IFG, which I think is an unknown functional gradient in this case. But more generally, what is really baffling, in my opinion, is that you have an AI system which was developed by AI researchers completely independently of neuroscience for very concrete purposes, which is to have something which allows automatic subtitling, for instance, or voice separation. And simply by following the rules that research engineers and research scientists came up with, this particular systems learns a hierarchy of computations, which seems to map remarkably well to the hierarchy of functions that we can here measure with fMRI. Okay, so this is with fMRI, which, as you know, is not extremely well resolved in time. But we can do the same type of analysis using magnetoencephalography. In this case, we did not focus on natural speech, but on a reading task. And this is data that was collected at the Dundas Institute, thanks to Jan Matthias Schoffelen and colleagues, where the participants read sentences one word at a time. So you have once, upon, a, time. You have 100 participants doing this task, 1 hour each. And what you see here is the average brain responses to word onsets. There is a lot of individual variability, but overall, if you average all of these brains together, you end up with the spatial temporal dynamics, which is expected, and nevertheless, I think, beautiful. After the onset of the word presented to the participant, about 100 milliseconds after this onset, you have a peak activation in the early visual areas, which propagates to the ventral and to the dorsal streams, recruit pretty rapidly SMA, pre-SMA, and the motor cortex, ignite the whole cortex, and ultimately fades within the temporal and frontal temporal lobes. Now, this is MEG, so this is source estimates, so we should always be a bit careful about the accuracy of these sources. But we can do the same type of analysis with intracranial recordings, where here 176 participants read words on the computer screen, and you end up with something which is very similar and remarkably distributed. And so while it's true, certainly, that with fMRI you can identify very specialized clusters for representations, overall, the whole brain seems to be activated in response to words, something to keep in mind. Now, these were average brain responses, but what is even more interesting is to look at the representations, so the sort of vectoral or the geometry of these neural responses at the single trial level. And so we do the same type of analysis that I showed you before with fMRI, but this time with magnetoencephalography, where at each time point and at each brain locus, we try to see whether we can find an encoding model from, for instance, a visual embedding, so a deep net trained on, in this case, captcha recognition. So we try to do this linear regression from a deep net to the brain and see whether it can find some similarities. So with visual embeddings, there is an effect which peaks in the early visual areas, around 100 milliseconds. This effect propagates along the ventral and the dorsal stream, and now you can see that it changes color. And it changes color because now there is an additional effect in the area which is cyan. There is, let's say, a blue effect and a green effect. There is a correlation with a visual embedding, and there is an additional correlation with a word embedding, which is a different type of AI system, which represent words as vectors. And this is very interesting because this area, not quite, I should say, I think there is some inaccuracies in the source reconstruction, but overall, this kind of region, as Stanislas showed this morning, have been associated with reading. And so here we can see with natural setup that this area seems to be transforming a visual code into a lexical code around 200 milliseconds. I'm going to show you this effect again, just as a loop. So what happens after 200 milliseconds is that the lexical code seems to propagate along the left temporal lobe and the prefrontal areas. And this lexical representation seems to be peaking around 400 milliseconds, which is historically associated with lexical access since the early work of Marta Kutas and many others since. But again, here we sort of see it directly through the lens of AI learned representations. What happens after 400 milliseconds is quite unclear, in my opinion. There's probably a lot of work to be done here. There seems to be a recurrent processing, but if you pay close attention, you'll see every now and then some peaks of reds. And ultimately, if we wait long enough, the whole brain turns red. And what this means now is that these brain areas or the neural activations seems to not be linearly predicted by visual embedding or by word embeddings, but this seems to be linearly predicted by the embeddings of language models, language transformers, the kind of architecture which is being used under ChatGPT and all of these modern language models. And the particularity of this particular type of algorithm is that they can combine words together as opposed to just representing one word at a time. And so if we wait long enough, it's seen that this particular compositional code seems to be broadcast and maintained, shared across all cortical regions that we can estimate with magnetoencephalography. Okay. All right. So one question that we ask with Charlotte Koster during a PhD is what exactly leads to this surprising similarity between AI systems and the brain? And so we trained a variety of language models using different objective functions. We varied their architectures, whether they are more or less deep. We varied their width, like how many actual artificial neurons we use for each of these models. We varied their attentional gating. We varied the amount of training. And for each of these models, we evaluated the extent to which the activations linearly correlated with fMRI and MEG. And all of these factors, these hyperparameter factors, to use the jargon of AI, do contribute to predict that a model and AI systems will tend to learn representations that are similar to those of the brain. But what's remarkable is that there is one factor which really stands out, which is the ability of the model to predict unknown words given a context. So if you have, let's say, a very shallow model, as long as it's really good at predicting the next word from context, its internal representation will tend to be similar to those of the brain. And vice versa, if you have a very deep model, which are now standard in industry, if this deep model is actually not really good at predicting incoming words from the context, these models will tend not to have representations that are similar to those of the brain. So that suggests that what really matters is the extent to which these models are intelligent. There is sort of an intelligent pressure for these models to create intermediary representations, which happens to be those that our brain found in the course of its development and of course, through evolution. I'm going to skip this set of studies for the sake of time. Okay, so because we have these similar representations between the human brain and these AI systems, you can do decoding. So how this works is pretty similar to the linear regression that I showed you before, except that we're going to do this linear regression in the other way around. So for instance, we're going to try to predict, given brain activity, the activations of the AI system. And you can make this a bit more fancy by using a deep learning architecture as opposed to a linear regression. Here we trained it with contrastive learning to try to maximally predict the most likely speech sounds given MEG signals in response to natural speech. And the result of this pipeline is that the algorithm, here the decoder, can tell you at each moment of time what is the most likely speech sound and what is the most likely words that the participant hear. And these are the first three subjects, which are pretty representative for a sentence which was actually cherry-picked, but not because of its accuracy, but because I thought it would be funny to make a reference to Eddie Chang, where the participant heard the sentence, "Thank you for coming, Ed." And you see that in subject 3, the decoder is perfect. All the words are accurately predicted. For subject 2, it does make some mistake. The first word, which is decoded by the decoder, is what and not thank. and the last word is in and not ed. And for the first subject, nothing is correct, in the sense that the most likely word given the decoder does not correspond to the true word heard by the participant. But the vocabulary is extremely large, right? You have 800 words in this particular pipeline. And so this is obviously extremely difficult to achieve a top 1 accuracy. But if you pay close attention, you'll see that the true word tends to be in the top 10, top 20 words on average. And so it suggests that you can start to reliably decode words from these real-time MEG signals. The cursor doesn't work. Okay. And finally, we apply the same type of pipeline not to language data, but to visual data, which was collected through the Things initiative, led by Martin Hebart, where 4 participants watched a bit more than 27,000 images through 14 sessions. So again, a lot of data per participant. But overall, we applied the exact same architecture, which I should say is open source and available. And the results have been replicated. The data is also publicly available for the previous study. And we just added one additional module to the alignment. So unlike words, which are a finite set, images are an open set. And so we added a generation module which tries to generate an image which is likely given the latent representations of a pre-trained network. And so the results that you see here at the bottom are the images inferred by this pipeline as the most likely given MEG activity. So it's not quite as good as with fMRI, but it's quite remarkably, say, there are some striking similarities. So here are some examples which are static. On the top is one trial, and the top left image is the true image that the participants see. The image is presented for 500 milliseconds, and each image is presented every 1.5 seconds approximately. And so we can try to infer the most likely image given MEG activity within the first 100 milliseconds and later in time. And when the participants see a panda, you see that you never get it right? The image which is decoded is actually not a panda, but it's a bear, which is black and white, which I don't think actually exists in the world, but seems to suggest that this decoder is able to pick up these really high-level semantic features and come up with something plausible. Similarly, for the bee, the decoder never decodes an actual bee, but it does seem to eventually decode a flying animal. And maybe just one more example, the last row is a bowl of sweets, of marshmallows. And ultimately, the decoder predicts a bowl of cheese, which from a French point of view is certainly a mistake. And if we look at more examples, it's quite striking to see both high-level and low-level similarities. It's actually extremely difficult to assess how good we are, because at a pixel level, we get close to chance level, and semantics is not really well defined. And so coming up with good evaluations for this training and these AI systems is actually difficult. But sometimes it does make mistakes that seems completely random. For instance, at the bottom right, you have a banana, and the object which is being decoded doesn't seem to share any low-level or high-level properties. And so in the case of fMRI, it seems, as I showed you at the beginning of the talk, to be even more precise. Now, of course, fMRI doesn't have the temporal resolution, and so we're hopeful to see how the two technologies will compare in the case of tasks or stimuli which are unfolding over time, which is often a critical component when it comes to reasoning or to cognition. So to wrap up, I think it's easy to get baffled by these technological achievement and to think, okay, we have AI systems that can process any kind of data. And certainly this will raise many concerns and potential clinical applications, which I'm sure we'll discuss. But from a theoretical point of view, I think there is something which is much deeper in the revelations behind not just these studies, but the studies that are similar across the field, which is that the principle or the reason why this works in the first place is because these AI systems tend to learn representations or functions which are similar to what our brain seem to be learning. And of course, we're not finished. These AI systems are limited in many ways. But from a formal point of view, it suggests that there are general laws or general principles that structure the functioning of intelligence, irrespective of the architecture. And that's, I think, a very important research avenue in the future. And I'm just going to thank again the students and the researchers with whom I have a chance to work, and you all for your attention.